And we're back for more POW coin, more proof of work coin here. If you're still following along with these videos, I applaud your steely determination. Let's just put it that way. So today we're going to try to kind of complete our network protocol. There's still some pretty big, there's still quite a bit of work to be done, and it'll involve a lot of just rounding off some rough edges. We're trying to kind of pull everything together here at the end so that we have like one coherent, 900 line piece of code that is basically Bitcoin. And lastly, we're going to be working on consensus, Nakamoto consensus, and chain reorganizations or reorgs. These are the mechanisms that allow two nodes to have a disagreement and for that disagreement to be temporary, for them to agree over time, which is really amazing. It's one of the true marvels of Bitcoin and one of the really novel insights of Satoshi Nakamoto. And so where are we? We are here. We are half-baked proof of work part one, or POW coin part one. We got a lot of work to do. I mean, this is it's kind of a mess, and we don't really know up from down at the moment. We got the munchies. It's we got a lot of work to do, and we gotta stay focused here. So exactly what do we need to do? So let's go down the list. We haven't completely specified how new coins will be created. To be honest, we can only mine empty blocks at the moment. So pouring a bunch of SHA-256 hash rate into empty blocks is just like completely stupid. So we're in this kind of like no man's land where we're like on our way to the final thing. But I just want to, let you know where we're at right now and how many things like are totally broken. Next off, there's no way to like join the network. The peers on a given node are hard coded at the moment, and so there's like no elasticity to who you talk to. If one of your peers goes down, you can't replace them. Moreover, and even worse, blocks are only propagated once. So you go offline for a little bit, well, you're screwed. You can't ever figure out what that block was. There's really no way to request a given block, right? Like you can in Bitcoin, right? They call it initial block download. You can download anything you want, and so our protocol can only transfer tiny messages. For example, a 1 megabyte message, which is not that small. It's like the size of a Bitcoin block. And when you're using the Bitcoin network programming, oftentimes you transfer quite a few more blocks than that. You send quite large messages. This would crash our server very quickly, and this is just because we're stupid about how we're reading bytes out of a socket, and it hasn't been a problem until now. So now we'll fix it, and it'll be you'll see exactly how when we try to do initial block download, you'll see like, oh, okay, it just clearly doesn't work. So next we have race conditions between the mining thread and the server thread. If you remember let me just run back. So this thing, remember that this is kind of our architecture diagram, right? We have this miner, we have this server, and they share some global variables. And if you look at the thing right below my cursor, I'm not going to move it because then that stupid menu comes back up. Beware, both threads shouldn't update same vars at the same time. We don't actually respect this very well at the moment. It's something we got to work on. We basically need to. In particular, what we're updating is basically the chain and the UTXO set. So what we're going to want is we're going to basically want to define like sort of like a baton like they have in track and field, kind of a baton that only one person can hold at a time. And so if the thread's writing to the shared global variables, it'll hold the baton, and then the mining thread just has to wait. And when it's done, then the mining thread can grab the baton. This is called a lock, is the specific word for what this is called normally. But think of it like a kind of a baton in one of those track and field relay races. Whoever has that baton can run, and whoever has the lock can write to the global state in a multi-threaded program. And so we have a handful of just general loose ends in the code. There's a few more than what I've mentioned. A bunch of little small things that are going to be honestly, they're going to be kind of annoying to fix. But hey, in software, that's you can't finish projects unless you do that final polish, and that final polish is really important. once those disagree with each other, they fork forever. Their chains fork forever, right? Like, so if me and you both mine a block at the exact same moment in time, right? We'll both think that our block is the best block. Well, how do you recover from that? At the moment, we can't. There's no good way. There's no consensus, is what it's called in Bitcoin. Lastly, there's no monetary policy, but that's for the next video, so we'll just ignore that for now. Monetary policy basically meaning really like defenses against inflation. How many coins will exist at any given time, and how do you prevent like both terminal inflation, right? You don't want your coin to inflate forever because no one will adopt it, and you don't want any sort of like near-term shocks of inflation. You don't want any sort of event to be able to cause the rate of issuance to explode. So there's two different solutions we'll implement for that, namely halvenings and difficulty adjustment. But that's for next video. And so that's just little overview of where we're at. And so let's start with this one, right? We can only mine empty blocks. That's a big problem. It's like we have a money, but it's like we define a money protocol, but there's actually no way to like create any coins in our protocol, so it's really kind of stupid. So let's try to solve that first problem here. Basically how coins are issued. So last time we said that we had this problem of Sybil attacks, right? Someone could spin up a bunch of nodes that they control that nobody else knows that they control, and that could sort of like overpower our network, and that would be bad. So what we did is we said, instead of just like having some sort of like a random oracle that could, and we also said that you can't have any sort of random oracle that can truly choose what blocks go in next. We said, okay, what if we basically awarded this block nomination privilege in a way that you basically, the privilege to nominate the next block would be awarded in proportion to the cryptographic proof of SHA-256 hash rate expenditure, right? So if someone's out there showing like, look at me, I'm just hashing like crazy, they'll get more of this privilege. If you're doing it less, you'll get less. But overall, we hope that it'll be competitive and no one will be able to monopolize it. But here's the thing, why would somebody be willing to consume such a costly resource for the right to basically timestamp transactions? People talk about Bitcoin as like a timestamping mechanism, and I didn't always understand what that meant. Basically what that means is it's not really talking about like what actual timestamp goes on the block. It's about ordering, like which transactions go in first. That's what you mean by timestamping. And so that's, this block nomination privilege is timestamping. Like, this is not that valuable. It's not that valuable for people to like dump all of the world's SHA-256 hash rate at it. So, how can we incent participation? How can we get people to dump all the SHA-256 hash rate that they possibly could find into this? Which is the case with Bitcoin, right? Like, all SHA-256 hash rate goes to Bitcoin now. It's insane. And so what we're going to do is we're going to, in addition to this block nomination privilege, basically this this transaction timestamping privilege, we're going to also award them money creation privilege. For every mining race, the winner gets a fixed number of coins. And what this will be is it'll be basically a way to make it so consumption of this resource is not like you're consuming this resource, but you're not really wasting it. Meaning, the protocol will give you back something, which if you sort of like buy the rules of economics and supply and demand and stuff, the price of coins would converge to the average mining cost, more or less, right? It's just kind of a common sense assumption. And so it's also an additive incentive not to cheat, right? Like the peer-to-peer nodes will always reject you, and now you have even more reason not to try. And so the way we're going to do it is we're going to create these things called coin-based transactions. So if you recall last time, at the top of the mining loop, the miner would say, the mine forever function. Let's just hop over to the terminal. So I'm in POWCoin, the subdirectory digital cash / POWCoin. Let's actually copy the code from last time and create a new file, just like we always do, and then we can start looking into the code. So POW Cinecoin, and then let's call it my POWP2P So POWP2P is like the solution file. And again, we put my in front of it, so it just like doesn't have any git conflicts. And this is kind of your copy. And so P2P coin, meaning like it's peer-to-peer, you can actually, anyone can join the network and do initial block download. And so let's open that. And we are in the text editor now. So now we're back in the text editor, and let's go implement these coin issuance, Coinbase changes we just discussed. So we're going to go to the mine forever function, because this is where, as we said, Coinbase transactions are transactions that miners basically give to themselves. And so, for that reason, let's go and look where miners construct blocks, and this is where we're going to have to update. And again, this is kind of naive. Like we don't have anything about, we don't have any block size limits here. You know, the Bcachers. I'm sure no Bcachers are left at this point in the videos. I'm sure I've alienated them, but they would be proud of this point, right? We just dumped the whole mempool in here. No, there's no limit at all. And so here we're going to want to, these are the transactions that go into the block, and so we'll want to add a Coinbase transaction to the beginning of this list. And the way we do it is just say Coinbase plus node.mempool. So we'll just create a new list that is the Coinbase basically at the front of the node.mempool. And so we just smash these two together, and this is a valid syntax in Python to do that. It's really nice. One of the many syntactic sugars that Python offers for the programmer's enjoyment. And so let's create the Coinbase. So Coinbase equals prepare Coinbase of we'll see what we need there. Let's just put some question marks. And so prepare Coinbase is going to be a function we're going to have to write. So let's go and stick that here below prepare simple transaction. This is something I created in the bank POWCoin thing, and this code I never really explained very well. This is basically how you prepare a simple transaction, and so we'll go over this a little bit, probably a couple times in the video, just so you guys there'll be some good opportunities to revisit how this works. But since preparing a Coinbase and preparing a simple transaction are similar code wise, let's put them together. So basically what we want to do here is just create a transaction and return it. So we can just say return tx, and let's fill in the 3 parameters that a transaction has. So if we look at a transaction, it has an ID, it has transaction ins and transaction outs. This ID is one of the little things we're going to want to change during the class, just as a heads up. So this is just like basically what we do now is we randomly generate IDs, and that's a waste of block space, because we could actually just calculate it dynamically based on the contents of the block, or the transaction, in the same way we do with blocks, and that would save us block space, right? If we can avoid having to stick any kind of random number generation to identify a given transaction, if we can avoid putting that in the blockchain itself, we save a lot of space. And so it's just, we're going to want to do that, but we don't really have a good way to test that change right at the moment because we're in this limbo state. So it's just a heads up. We'll do that later in the video. But at the moment, there are 3 parameters for transaction: ID, transaction ins, and transaction outs. And so we'll need to define those 3 here for prepare Coinbase. So ID is equal to, let's just say ID. We'll have to, let's just create that right here. So what I'm going to propose is, you see how right in this line is where we create the transaction ID for prepare simple transaction. This is uuid.uuid4 is just I'll just show you. So I'm just in can I clear now? uuid.uuid4 just basically creates this random string that has a specific format. And so yeah, that's what we're using as IDs at the moment, and it's not perfect, but it's pretty good for as random IDs go. This is a pretty convenient thing in Python. So this is what we're going to do. So let's just copy that, So let's just say txid equals txid, right? And so we have an ID now for our newly created Coinbase transaction, but hint, hint, well, we'll get to that later. So TX ins, and we'll just say they're empty right here for the moment. And so the way a Coinbase is going to work is it's going to have one input and one output. The output will be like a normal looking output that our code will be able to handle just like anything else. It basically says like, you know, remember the TX out has 4 parameters at the moment. This is also something we're going to need to change. This is actually redundant. We don't need these 2 in TX out. Again, my mistake, but we'll get to that later. And so these are the 2 important things in an output. It's how much and to who. How much is the amount, to who is the public key. And so you could also think of this as like how. This is like the puzzle that someone needs to solve, sort of to unlock the output. They need to provide a signature that matches, that, you know, was signed with the private key corresponding to this public key. And so at the moment, you know, it's the ID and the index are going to be, ID is going to be this ID, right? Where did it go? Yeah, so ID will be this ID. Index will be 0 because it's first in the list. Then amount will probably be something that we'll have to get like a fixed number. Let's say just like block. We'll make a fixed variable. It's not a variable, like a constant that is called like block subsidy. That's what I propose. We'll call it block subsidy, and that's so like every block someone gets a fixed number, maybe 50, because that's how Bitcoin works. It was 50 Bitcoins in the beginning, and so and the public key would be something we'd have to probably pass in as a parameter here. So this would, you know, when you call prepare Coinbase, you'd give it your public key. So and so TX ins would be basically, they'd all be like all the parameters in TX in, like these don't exist because there's no TX ID of what you're spending. There's no index of what you're spending because you're just creating these out of thin air, and there's no signature to sign because like where the money comes from is basically the protocol itself, not from a previous input, not from a previous unspent output that is being kind of reassigned to you, if that makes sense. So let's just go and code this up. So this will just be none, none, none. And they're all none because there's no, you know, the TXN specifies these first 2 parameters are which output you're spending. Well, Coinbases don't spend an output. They're just like magical money from nowhere. They're just part of what the protocol gives us for finding this, the right nonce in the mining race. And then the signature also, you know, wouldn't exist because that's sort of like the, you know, how the previous output is unlocked normally. But we will, you know, one thing we could do is just not include it, have the Coinbase have no inputs. But eventually we will want to have one, we'll want to be able to stick some data in here just to make sure that our Coinbases don't collide with each other, just to make sure that we never have the same TX transaction IDs. And that'll be, once these transactions are hashes, that'll become a problem. Right now, we inject enough randomness in here by giving them random IDs that they're, you know, they probably won't collide, but eventually we'll want to do that. So that's why we're going to leave this in here, and we'll get to that. And so then for the outputs, this is how they'll work. Let me just type it out. So first we'll want to grab the transaction ID, which we already have, then the index, which is 0, and you can just look over here. This is, you should recognize all that these are just the parameters that go into TX out. And hint, hint, we're gonna actually delete these 2 later on in the video. They're not necessary. There's just a smarter way to do it. And so amount equals, let's call this block subsidy. Will just be a constant that we'll redefine here in a second. And let's go make a new line and then do the public key. And the public key is not defined yet. So we're going to want to, you know, this would be the public key of the miner, right? This basically is the miner paying themselves. And so we're going to want to pass this in as an argument. So if we run down to, if we then go down to where this function is called, so remember we put some question marks in here because we didn't know what we'd put in. Now we do know. It's got to be public key. Public key here does not exist, so we're going to have to pass it in once again as an argument. So like when mine forever is first called, we're going to want to stick in. And so when mine forever is called, we're going to want to actually call it with a public key. So let's go look for it. And so here we'll want to throw in a public key here as well. And for that, let's just stick like a to-do in there. Well, here I'll just show you how to add an argument. So this is how you do it in threading. You just say args equals the list of your arguments, because you're like passing in the function. Target is the function you want your thread to run, and then args is the arguments you want to give them. And let's just say public key, and then let's say to do. At the moment we had this, if you recall, we had this identities.py file. It was just like the stupid file with some identities that would exist in our program, and it's really kind of hacky and crappy. So I'm gonna, towards the end of this, once we actually run this, you know, in 10 minutes here, when we actually run this, I'm going to, if I remember, I'm gonna go and create a little bit better way. Okay, so we'll just leave that to do in there, and we'll cover that when we actually go to finally run the code. So the next thing we do is we need to actually define the block subsidy, that constant we made. And so we'll just say block equals 50, just like Coinbase, or sorry, Bitcoin was at the beginning. And it's just like a simple number. You know, next video we'll add like Satoshis in our protocol so we can have a really divisible coin. So, but at this time let's just call it 50. So next, let's look at the handle block function. This is what we'll do validation on our Coinbase transaction, in which we'll sort of sync it to the UTXO database, update the UTXO database, the UTXO set based on this transaction. And so the rules for validating a Coinbase transaction are clearly different from a regular one, right? The validation code for a regular transaction here is basically checking two things: that no money is created or destroyed, and that the signature is correct. Neither one of those apply to Coinbase transactions. We want to make sure that their amount is a fixed amount that we've kind of observed, that we've all agreed upon, which we're going to call the block subsidy, and that's it. And so let's write a separate function, or let's just write it out here. So like, let's say so we'll validate the Coinbase separately, and then we'll want to skip it here when we get to to do the normal validation. So we'll just say this is a Python syntax to say start at index 1, so skip index 0, and iterate through everything else. And so this is a way to just skip the Coinbase transaction when we're doing traditional, like, or normal transaction validation. So the next thing we want to do is we want to actually write the validate Coinbase method. And so this code up here is for validate transaction, so let's just stick it right below that. And we'll just assert that it contains only one input and only one output, and that the output's amount is the block subsidy. That's really all that matters. And this is the way you can do it. You can just say, we can just cram this all into one line. You can do this like multiple, you can have a couple equal statements in one statement, and let's just say they're all equal. The lengths are both equal to 1, and I think that's a little more readable. And let's just say let's look at the output right? There's only one output because we just asserted that. And let's check the amount, and let's just say that's equal to block subsidy, right? And so the thing we really want to avoid here is people, giving a Coinbase transaction themselves, which is like has 1 million coins or something. That would really be, inflation is the bane of digital cash or cash in general, and so we really want to avoid that. And so now, if we go down here, we've written our method, and we can accept this transaction, and it'll get verified. And so now we can look down further in our handle block method, and we'll see here the next thing we do is we update we iterate through every transaction and basically sync that transaction's changes sync the transactions inputs and outputs to the UTXO database. We delete the old outputs that were spent. We save the new outputs that were created. And so if we look at that function, here it is. And so, yeah, deleting the old ones that were just spent, creating the new ones that are now like the balances that now are the kind of the coins that exist, the outputs that exist. And so what we're going to want to do here is so if we go to our shell here, we'll say for Coinbase's, the out point will always be none, comma none, or the tuple none, none, two nuns, because that's the TXID and the index are both none in Coinbase's. If you recall, where is it? Right, prepare Coinbase's. So these two would be none, and so that's what you'd get for this out point. So you'd be deleting none none from a database from a dictionary that should never have none none. And so if we just simulate this over here in Python, we'll say, like, pretend we have an empty dictionary, and we'll try to delete an item D of A. That's our key, a key that's not in there. Or we could just say, this is like what we'll be doing here. We'll get a key error. That key's not in there, can't delete it. And so that's what we want to avoid. So we'll want to say here, every time we're going to want to check, if not, we can probably stick this out here. If not tx.isCoinbase, then we'll want to iterate through and delete all the things that were just spent. But if it is a Coinbase, ignore it, because there's really nothing, there's no like UTXOs sitting in the database that were just spent. All the coins that will be created here were like created out of thin air because it's a Coinbase. And so we'll want to now define this tx.isCoinbase. So let's run up to transaction class, and we'll just stick it at the end here. So at property, just like normal, because it's sort of like we like to think of it as like a static attribute. Doesn't have like the API of a function call. It's just like an attribute on the class, on an instance of the class. And we'll say def is Coinbase of self and return self dot. We're just going to check if the TXID of the first input is none, and that's enough to identify whether a coin is or is not a Coinbase or not. And so yes, that should work. Okay, so it looks like we pretty much have this covered. Like, there's no more Coinbase related things that would happen in handle block. And so the next thing we got to do is update mine genesis block. So mine genesis block over here on the right, just getting move left to right here just to keep it up, just to keep just to mix it up a little bit. So yeah, with the genesis block is a block like any other, and it requires a Coinbase transaction. But there's going to be a small kind of complication here, and that's that we won't be able to randomly generate the ID of the Coinbase transaction. We'll want to do something more like this. Let's just, for the time being, until we get to the point where we can where transaction IDs are a hash of the transaction. We have to keep passing in transaction IDs. Let's give it away. So prepare Coinbase. If we tell it an ID, it'll use that ID instead of a random one. This way, if 3 different nodes when they all kind of go and create the Coinbase themselves, they will get the same one. And this is kind of a hack. Like, we could hard code a Coinbase transaction, but it's like really inconvenient at this point when we're still changing things all over the place. So like, if we went and, if we had a hard coded Coinbase from the last video, now we're going to change a couple things. We have to like re-hard code the Coinbase. It's just kind of a pain in the ass. So it's better to have everyone just kind of mine their own Genesis block in a way that's deterministic, so they'll all mine exactly the same nonce and get exactly the same block, the same ID. And so again, we'll have to say public key. We'll have to pass in public key to the mine Genesis block. This basically means like who gets credit for it. And this is a bit of a hack. Like in a real network, somebody a first person would mine this, and this is a bit of a hack just for demo purposes. And so we'll just say that like Alice is Satoshi. Alice gets the Coinbase or something, or the Genesis block. And so now before actually implementing this and prepare, well, actually, let's go ahead. Let's go to prepare Coinbase and let's just implement this. So we'll say, so we'll give it a TX ID and default variable of none. And so we'll check like if the user didn't hard or override the value by actually passing in a TX ID. Then we will, if they failed to override none, then we will pass in we will generate a random ID for them. And this is the simplest way to do this. You can't actually say like, because this will just get, like when the program loads, this will evaluate once, and then it will give you a random ID, but every time you call this function, it'll give the same random ID. And so you want a different random ID every time. And so this is a way to do it. Just give it a none and then pass in UUID dot just, if they fail to override it, then give them a new one. So now we have that covered. And so we're back here, and so what we want to do is we want to actually pass in the Coinbase to the transactions. And then lastly, what we want to do is we want to say node.update UTXO set of Coinbase. So this would basically just have the effect of creating a new unspent, our first UTXO in the UTXO database based on whoever mined this Coinbase. And so this is a bit of a hack once again, but it's just like a simple way while we're developing our code to avoid having to hard code something and always update it. And so long as we pass in, as long as all our peers pass in the same public key, then they'll all generate the same Coinbase transaction because we've hard coded in this transaction ID. And so if all this is the same, they'll generate exactly the same block, and it'll have exactly the same block ID. And so then when they all start mining on top of that, they'll basically all have the same first block in their chain, and so they'll be able to come to agreement about whose chain is what. Obviously, if everyone had different IDs for the Genesis block, you'd never be able to come to consensus because there's no shared block anywhere in the history. And so now we're finally at the point where we're getting ready to try to run this thing. Now we're going to try to run this next iteration of our network, which can actually produce. It actually has like some money. Like previously we had this blockchain, but you can't. POWCoin, we have this blockchain, but it's like no money is ever created because we didn't have a way to do it. And so now we actually have a way to create money. And with every block that's mined, we will create money. And so we had this kind of to-do down here, what is the public key of the miner? That's basically the one thing we have to do. Before we can spin up a mine, and we have to be able to say, like, this is the public key we're going to be mining to, right? This is where we want the UTXOs to be where the UTXO checks to come, so to speak. And so to do that, I want you to go over and look at the POW p2pcoin.py file. That's where like the final version of this is. And so what we're going to do here is we're going to just copy this code. It's not really important that you understand what this is. These are just like These are just two little utilities to, this is right before the main function. These are two little utilities that can just like look up public and private keys for a given kind of like name. And so our sort of universe in this little demo has 5 users. We have node 0, 1, and 2, right? And then we have Alice and Bob. And so what we do is we have this dictionary where they each have a name and then a number. And then so we look up, the lookup private key just takes a name and it just looks up that name in this dictionary. And what it gives you is a number, and so that number is used as like the secret exponent to spin up a private key for them. So that, you know, when we run this program twice, Alice will have the same private key both times. I mean, it's just like, I guess not super necessary, but it's better to do these things in a deterministic way. And so all that lookup public key does is it just calls lookup private key and calls get verifying key, which is basically the public key. And so those are two little hacks that we'll be able to use. And so what we'll want to do is we'll want to say like, let's just say like name equals os dot. Let's just say that we have like our node has a name, and we will update our Docker compose.yaml file. We'll actually make a new one and we'll include this. Like previously we were doing this like ID and node ID. We're just going to go name. It's simpler. And so what we're going to say is, let's just say minor public key is equal to look up public key of name. And so maybe we can stick this at the top of the file, and then minor public key would maybe go right here. And then so instead of just public key, we'll say minor public key. So there we go. So we have a public key now. This will look up a public key in a deterministic way based on whatever this name variable is for this node being, you know, running within Docker. And remember, we have 3 different ones: node 0, node 1, and node 2. And so they'll all have different public keys. So they'll be all kind of mining towards their own balance, which is pretty cool. And so lastly, we need mine Genesis block. We want to mine the Genesis blocks. Let's just say Alice is Satoshi. So let's make a note. Alice is Satoshi. Okay, no, mystery solved. Okay, there we go. And so we'll just say look up public key of Alice, and that will just look up that'll, you know, up here that'll call lookup private key, which will just get the number 1. It'll turn 1 into a ECDSA private key, and then it'll turn that into a public key. And so this will give us so you can see, like, code readability wise, I think this is, again, there are a few of these hacks going in, but they're, we got to capitalize Satoshi, of course, good Lord. There's some kind of hacky things, but I think they're still, they help kind of understand what's going on. And so lastly, if you recall, we had this like file identities.py, which had this crap that was similar, but like look at how much more there was. There was all this crap. And so we just replaced all that basically with these 6 lines or 8 lines. And so what we're going to want to do is search for identities.py. We were using user private key, user public key. We were still using these. And so we're just going to delete those lines and just search for user underscore, and you'll see there's 3 places we're using these. They were all user public key, user private key. So we'll just say replace user public key with lookup public key, and then user private key is just lookup. And so now there's no more user underscores. So we've just eliminated this ugly relic identities.py. Good Lord, what's that? And so that's good. So I think we're at a point where we can probably run this now. So the last thing we need is I want you to take a look at this file. What is it? So Docker compose p2p.yaml. So I just updated it just a little bit, and so the one thing that it's going to have is it's going to have, I just changed the name. This used to be an ID. So see, this was like ID and like a 0. I just think it's easier. I think it's simpler in your head to think of just pass this in instead of the ID. Just pass the whole thing in, so we're not dealing with like some random ID numbers that are just weird. So yeah, that's what this is. And so when we run this now, like let's try to run this. Hopefully it'll work. So we go to the terminal here, and we're in POWCoin directory, the subdirectory of digital cash. And so what we're going to want to do is docker compose. We're going to want docker compose -f docker compose p2p.yaml -s build. And -f just says use this docker compose.yaml file, this docker compose file, this set of configurations. And so we can't, and we need an up in there as well. We want up after, I think, the -f. I don't sure. You could probably do it before or after. We can't just like edit the docker compose file, because actually the POW Syndicoin uses that. And so like I'm always like trying to juggle backwards compatibility, because we're going to have a lot of students running through this class, and they all have to be you know, it has to be completely backwards compatible, which is really hard. It's weighing on me. So let's try this, see if it works. Be surprised if it does. Oh, sorry. I think we have to edit the Docker file too. Right. So this has the POW. We want to put my in front, and so do that both places. And you'll notice I put this -u. So apparently sometimes Docker would eat exceptions. Like there'd be an exception, you wouldn't see it. And so this -u basically makes you see those, which is really helpful. So yeah, that's if you hadn't seen that in previous versions, that's where that came from. And so let's try it now. You'll see it did copy my POW p2pcoin.py, so we are working with the file we want. And so there we go. We just mined a block. The difficulty, I think, is at like 20 right now, which is pretty hard. It's like 8 times hard. Like I usually set it on 17, and so yeah, it'll be a little slower. But what we can do here is we can source our virtual environment and say Python my POW p2pcoin.py balance. Let's just say node 1, or let's say Alice. And look, holy Lord Almighty, that even surprises me. It says 50. And so let's say node equals node 2. I think that should, oh, look at that. Good God, this is amazing. This is amazing. They all say 50. They all say Alice's balance is 50. And so that, like, notice this was impossible at the beginning of this video. There were no like monetary balances anywhere. Look at Bob. Bob's broke ass. Look at him, poor guy. And let's see. So let's see who mined the first block, node 0. So so the first thing I'm going to do. Oh, so node. So look, node 1. Node 1 broke. Hasn't mined a block yet. Node 0 got 50. He mined a block. Node 2. Also 50, right? Because node 2 mined a block. So look at this. Like, good God, how rewarding. We now have our digital cash protocol, which started at the poor and just really pathetic. And now look, so now it's 100 now because node 0 just mined another block. And so now we are actually creating, you know, our poor digital cash project, which started with frickin', I want to say the F word there, but this is a YouTube, so I'm going to tone it down. So PNG coin, now we are like from there, now look at this. This is like almost Bitcoin. This is really close. And so sweet. Now that this is working, and that was quite a bit of work, to be honest, let's kind of move on to the next part of the project. So we have Coinbases, right? Like yippee, we did miner subsidy. We have like this miner subsidization that miner subsid. I don't know how to pronounce that, but we have this way of subsidizing miners for their expense, in theory, so that they would basically give us this block nomination function in a way that they don't lose money if so long as the Bitcoins become monetized, or our POW coins, excuse me. Okay, so now we're ready to make make our network sort of like joinable, make it so that people who are, or nodes who don't have kind of a hard-coded connection in our Docker Compose file are able to discover peers they might not know about and connect to them, and to connect to the ones that are kind of hard-coded, the kind of seed connections that we give them to begin with. And so this is going to be pretty similar to how Bitcoin works. In Bitcoin, it's called the version handshake. In every one of these protocols, there's some sort of a handshake that two parties engage in that establishes the connection. TCP/IP, the base layer of the internet, has a similar thing. And so yeah, this is how ours is going to work. I mean, it's not perfect. It's kind of a little naive in places, but it'll do the job. And we're trying to just get the general idea. We're not trying to cover every corner case and make it perfect, right? Like that's not the purpose of this little project. So we're gonna have four new messages, right? The first one is gonna be just called connect, right? These are the network messages. Remember how we had like block message, transaction message, these things that we could send to each other. Ping was their first message, and then pong was the response. And so here are four new ones that we're going to add. So the first one is connect. This just says, hey, you want to be my peer? And that's all it is like, hey, maybe we want to do a connection here. And then the response would be like, yeah, I will accept your request. And actually how it's going to work is that once you get, there will actually be kind of like two of these. So if you send a connect message and then you say, hey, can we be friends? This one will say, yeah, we can be friends. And then you'll send back basically a confirmation like, okay, yeah, we can be friends. So both sides will send this one. And when you send this one, you will add the other guy to your peer list. And there's a diagram about this in the next slide. So if that doesn't make sense, don't worry about it. And then once you have a connection, we'll add this new message called peers, and this will just be say, hey, could you tell me all the peers you're connected to? Maybe I don't know some of them. Maybe I'd like to meet some of them and to establish connections. And then this would be the response saying, yeah, here's everyone I know about. Maybe you can try connecting with them. And here's a diagram of how the handshake protocol will work in more detail. So node A, node B. Node A is trying to connect to node B. So it sends a connect message, and in technical term, in implementation detail, this means that node A will add node B to its pending peers list. It'll have two lists, peers and pending peers. Pending peers is like the ones you're trying to connect to, who you have like an incomplete connection with, and peers is the list of the people who you are connected to. And the reason why we have two is basically anytime we receive, well, I'll explain it in a second here. So first we'll add it to pending peers list, and so when node B gets this message, they have two options. They can either ignore it, say like, screw you, I don't want to connect. If you do, you'd send a connect response message, and as you do that, you would add node A to its pending peers list. So each side has this as like a pending connection, and then so when the way it works is like when you receive a connect response message, this is like confirmation. This is like, hey, confirmed. The other guy said confirmed. We're good to connect. And so what node A will do is it will move node B from its pending peers to its peers. And so the same thing will happen. They will send the same message again saying like, yeah, confirmed, we're good to go. And node B will do the same thing. It will move the other guy, node A, from pending peers to peers. And so you might ask, why do we have peers and pending peers? when you get one of these connect response messages, you want to know that like pending peers is just a way to quickly look up whether we intended to connect to these guys in the first place, right? We don't want to just, if we get one of these messages from node C who we've never heard of, we don't want to just like add them to our peer list, right? So pending peers is just like a way to look up whether in the past we have intended to connect to them, right? This is just a way to, like, when we get this connection confirmation, just check that we were interested in making this connection at all in the first place, right? And so if we pick it up back over here, so now we have a connection on both sides. Both sides acknowledge the other one as a peer, and then so what is optional, it's not required, but what's optional is that you could go and node B, for example, could go and request the peers of the other guy, right? And so you'd request peers, node A, using the peers message, node A would say, hey, these are my peers, and then node B would kind of iterate through them and then issue a connect message to anyone it didn't know about. And this could go both sides, right? When this guy receives its peer message, when this guy receives this, connection response message, right after it sends connect response, it could also send its own peers. So basically both sides will exchange the peers that they know about. That's not super clear from the diagram, but I mean, I'm spending enough time on this, so I'm not going to fix it or improve it at all. But both sides will be able to go say, hey, who do you know about? And they'll just be able to kind of ask each other until all peers are known by everybody if they want to know all peers. And so yeah, let's go and implement this. Okay, so we're back in my POW P2PCoin.py, exactly where we left off last time. And first off, we're going to look at the node class. And we're going to, I don't like this variable name, peer addresses, so I'm just going to propose, let's just call it peers. Sorry, we refactor like this, I just wanted to make it simple, and I like a nice short variable name, just kind of reduces typing. So I'm going to, so every instance of peer I just changed to peer address, I changed to peer addresses, I changed to peers. And so that's a simple start, a move to get us going. And so the next thing that we're going to do is where we previously just read these peers from the environment, I want to, I'm going to just set it as an empty string, and let's go to the bottom of the file. We're going to want to use this eventually. So I'm just going to copy that code that we had there. I'm just going to comment it out, because just so I don't have to type that again. But we'll be roughly using this code when we want to actually go and connect with peers. So the way it works, this change basically makes it so we don't have our node connections aren't hard coded. We don't just read them from the environment and hard code them. We start with nothing, and then we have to manually add them. Okay, so the other thing we're going to need is the self.pending peers is another empty list. And so now we have all of the sort of mechanics on the node class itself, all of the places to store information to handle this. So let's go and write a connect method. So def connect. And so peer would be the guy you want to talk to. And so the first thing that we're going to do is make a check, and we're going to see if we already know about the peer and if the peer is ourself, right? We don't want to be connecting to ourself. That doesn't really work. So So we'll need to create self.address, so that's kind of a mental to do. And so the first thing we'll do, let's log saying that we're trying to connect to them. And we'll do a fancy little log here. We'll put parentheses. Oops. What every once in a while I'm like hitting my page down key and it just wrecks me. So we're going to want to let's just put handshake in parentheses at the start of our log statement, just to say, like, just what sort of stands out, because it's sort of like a very different thing. The rest of our protocol and all the rest of our logging has like a very different meaning. So this is just a way to make it sort of stand out visually, put parentheses and sort of a little context for these log statements. And let's do single quotes because we're gonna have double quotes inside. So sent sent connect to peer of 0. Peer of 0 will be like the IP address or the host name. It's like the host name, right? So you have a host and then a port. So we don't want to see the port name because it's just a number. Remember, a peer is a tuple, so it's like IP port, and so that'll just be kind of log like, hey, we're sending a message, and then what we're going to do is try. We're going to try to connect to them. And the reason, usually when we send a message, we don't use a try and accept, right? We just assume that it's going to connect because we kind of assume that our other node is online if we're trying to connect to them. And so, but here, just because like when we first turn on our Docker Compose thing, only one of our nodes, one node will wake up first, and it'll try to connect, and the peers will be offline. So I think it's kind of nice to do a try and accept here to attempt to connect, and then if it fails, we'll say, hey, the other guy's not awake yet. So it's pretty simple. We just say, hey, connect to our peer, so send a connect message to our peer. The payload is none because there's really no other information other than this like declaration of intent. This message just is what I intend to connect with you. Are you down? That's all it means. And then we'll say, we'll add it to our pending peers. And so our pending peers is just like kind of like a whitelist. Think of pending peers as like a whitelist of all the people we're kind of okay with connecting to, just so that we just want to, I think it's important to understand that, you don't want to just be accepting random connections from anybody. You want to sort of like have just a few peers and that works. And so, because, peer-to-peer network, some nodes will behave badly, and you want to manage who you're connected to, right? You have to assume that people are going to behave terribly, and so you always want to have a defense against that terrible behavior, and having this peer list, this list of active connections, and this protocol for establishing connections is our defense against that. And I think that's really kind of vital to understand in terms of how a peer-to-peer network works. And so we'll do those two things, and then the accept will basically mean like our attempt to send a message over a socket failed, and in that case we'll say logger.info, and then we'll say handshake again, and then we'll say node, we'll say node node offline, right? So I think that'll be this looks pretty good. We send a connect message, and we manage, we add this peer to our whitelist, and along the way we do a check. We just make sure if the connect is, the attempt is like kind of sane, and we could maybe do this check somewhere else, but I think it just makes sense to stick it here. And we do a little logging along the way. So it's a pretty concise method that actually does quite a lot. And so we have a couple loose ends here. We don't have self.address yet, and so let's kind of get that figured out. So what we'll have to do is we'll just have to pass in address to the class. This is kind of crappy. I wish we didn't have to do this. I wish like our architecture was smarter so that our node class had a little bit better understanding of what its own its connection to the server. So like in version 2 of this, like I'll refactor this someday, and we'll improve all this stuff. I'm just trying to ship something that's pretty good. We're trying to get like a 90% of the way there, and there's some rough edges, but this is kind of ugly that we have to do this, but I think it'll work. And so what we're going to do here is just how we looked up name, remember last time? So we'll be able to pass in address. So it's actually like, it's kind of ugly, but it's really concise at least. So this is all you need, right? Name is basically like the host name. So host name comma port works to establish a connection. So this is kind of like, it's nice that we can do this. So yeah, so we try to so we check if it's connected or not, and whether we're talking to ourselves, because a connection to ourselves wouldn't work. And so now that we have a connect method, we need our server to have a handler for this. So if we go over to the other side here and look at our TCP handler and the handle function, this is like the part of our server that actually handles commands. What we're going to want to do is we're going to change this thing a little bit. We're going to basically break it out into two connections. We can delete. We'll just comment that out. I think we're going to move away from that, but. I'll say handshake and authentication, and down here is like business logic. Yeah, that's good. And so how it'll work is like if command okay, so and we'll just say peer. We'll have to say what peer is. So this is going to be what the structure is like. It's going to every time we get a message, we're just going to run like some authentication code. We're going to like check, hey, if these are the only two things we check if it's a connect or a connect response, and if it isn't, we're going to say like, hey, our peer better be in node.peers. So this is basically going to reject anybody who isn't currently connected to us. So this is great. We don't have like randos sending us blocks and transactions that we try to handle. We only have to deal with people that we've or nodes that have behaved well and who are willing to kind of do business with, so to speak. And so yeah, and then the rest of it, like if we're able to pass this assertion, then great. We can continue with the other logic. If one of these is true, then the rest of this won't be true, right? Because these are all different commands. So if it wasn't one of these two commands, we're going to enforce authentication. So yeah, this is kind of the outline. So let's go forward and fill in the details. So first thing, let's say what peer is. So peer in this socket server thing we're using, it's self.client address. That's the basically the tuple of IP and port, the address for our peer. And so for a client, and so now we have that for here at the very least, right? This is where we use peer here, and so we'll use it a few more times. So the first thing we want to do is say, if we get a connect message, we want to check, hey, we want to make sure that this peer is not in pending peers, and it's also not in peers. We want to make sure that we have no relationship to the peer that just sent us a request to connect. So this is how that'll look. If peer not in node.pending peers and peer not in node.peers. So a little verbose, but I think it's pretty understandable what we're doing. We're just checking that we have no relationship with this node. And then we'll add it to our local peer, our pending peers. We will log what we just did. We can maybe, we're kind of getting heavily indented here, so it's getting ugly. Okay, so this is becoming not very Pythonic. That's okay. So we'll say accepted connect request from peer, and then lastly we'll say we will send the connect response message. Remember, so we just got this, so we're going to add it to the local pending peers, right? That's what we did here. Added the peer to pending peers, and then we sent a connect response, right? So send a connect response, and then we just log. So and so it's kind of at our discretion when we accept these. We could add more, and kind of exercise for the student here. You could add more conditions, like maybe you want to have a max peer variable, and you want to check that. If you have 4 active peers, then you'd reject. Like you could make this condition as strict or as liberal as you want. You could maybe accept every peer. This is kind of up to the individual implementation what you want to do. And so and maybe you could think of it as like a configuration detail. This is something that different users might have different views on, right? And so next, let's handle the connect response message. So we'll delete the ellipses, and we'll basically do this. I'm just going to copy this line. It's going to be basically the same line, but we're going to say if node in pending peers and peer, or if peer in pending peers and not in node.peers, right? So this is we want to ensure that the other guy's in like a connecting state, right? That we actually sort of like started the handshake with them. We intended to, we expressed our intent to them to engage in this handshake to establish a connection on the network, but we haven't actually done it yet. We haven't concluded it yet. So handling this message is basically how you conclude it. Once you get one of these, it's like, okay, done. And so if if this is true, we'll say remember, because we're going over here, we'll say we're going to move node B from pending peers to peers. So that's what we're going to do. We're going to remove it from peer or from pending peers, and then add it to peers. Then we're going to log what we just did. We'll just put quotes around it. Yeah, connected to node 0. And we'll do that up here too. It's just nice to have quotes around the stuff. It's just not important, but I think it'll make it look a little better. And then, so lastly, we're going to do this. We're going to say, hey, we're going to do this. We're going to say, hey, who do you know? Right? Who do you know? You're always in this Bitcoin network programming. You're always kind of paranoid that you're missing some information. You're missing some peers. So it's this kind of the way you can think of your node is like it's just this like paranoid schizophrenic who's just like always looking around, making sure it didn't miss any information, that it's got the most up-to-date view of the network and of the blockchain. Okay, so there we go. I'm sure there's a typo in here somewhere, and it's not the prettiest code, honestly, but like I think it packs a pretty heavy punch. Like we just added authentication in like 10 lines of code, and or 20, and I think it's a really essential idea to the network. Like I spent a lot of time figuring out how to present this and making sure it seems kind of good. So so before we move on, we're going to kind of leave this. We're going to be sending this, but no one's actually going to be there to respond to it. And so I just want to show you what it looks like if we run this without actually responding to the peers, you know, in order to like what it looks like if we don't let the graph totally fill out. And so we'll need to just we'll need to go down to the serve instructions in our main handler. Oh man, it's raining. It's just pouring outside right now. It's a beautiful sound. So what we're going to want to do here is we're going to want to remember this code that we deleted and saved here. So we're going to want to move that, and we're going to want to move it. We could put it anywhere. Let's move it right after we start the server. So we'll just say join the network. And so what we'll want to do is, I'm going to simplify this code a little bit. So this was a set comprehension, and this is something this is like the exact code that how TinyChain, the other thing, does. I try to make it a little simpler. So like I try to remove all the sets and stuff because it's just like not necessary. So this will actually work. So all this does is it goes and iterates through the peers attribute. That you can, we need this. So it goes and grabs the os.environ.peers attribute, and this is just from, so this is just this, right? It just grabs this string, node 1, comma, node 2. It just grabs this and it splits it on the comma. All right, so that's all it does. It just gets a list of all the things that the commas separate, and then for every one of those, that's a host name, like node 1, node 2, node 0, and then it just packages them as addresses, as like host name, comma, port tuples, and so we'll call this peers, and then we'll say for peer in peers node.connect. Boom, and that's all it takes. Look at that. So I think we did a pretty good job here. It's simple. So we were able to just grab the peers from basically our configuration file and attempt to connect with them. So like big difference from last time, right? Last time we were just like on our class, right? If we look at this one, if we look at like last time, we just had it on the class, just hard coded. It was just read hard coded here. Now we're actually going, the only way to update the peers now is to go through the protocol. We have to actually go through the handshake, and the other guy has to actually let us in the door. And so that's so yeah, I think that's a pretty big improvement. And so let's try to run this sucker. I'm sure I made some typos, and I'm sure you guys see me do the typo and just shake your head as you have to continue following along. But hey, I got it's not easy. So let's run this. Well, here, let me. Remember, we're going to use this Docker compose P2P. So that looks good. And Vim Docker file, edit anyways. Yeah, so I'm over here like testing stuff like crazy. This is going to be like the solution file to this little section. So I'm just like my POW P2P coin.py. Yeah, so that looks good. So this you shouldn't have to do this, but I'm like a cowboy over here, so. Oh, and we got a little syntax error, so yep, so I didn't quite do that right. So I was changing it from a list comprehension to a set comprehension, and I only fix it on one side. And we're actually gonna I'm just going to, instead of using this .get, which is like a fancy thing, let's just look it up like let's just assume that this exists in our os.environ, because it's like we're just going to always have that in there. So yeah, that's just a safe assumption to make. .get will just basically return an optional value if it doesn't find anything, and that's what was happening here. It's like if it's not there, we'll give you an empty string, and then when you split it, it's just like an empty list. Okay, that was and so that's one more thing I neglected. We also have to whenever you receive a connect response and say yes to it, you send one in return. So it's like I confirm, and if it's the first time I've confirmed, then I confirm back to you. And so then we'll say so that's important. Just kind of glossed over that there. Sorry about that. And so if we run this, this is what it'll look like. I ran it, and so our node 0 finally, like node 0 wakes up first, then node 1 wakes up. Node 1 or node 0 says like I'm going to send a, or excuse me, node 1 says I'm going to send a connect message to node 0. Then node 0 gets it, and it says okay, I'm good. But all of a sudden it's like this is the address we're receiving it from. So what we would really like this to say, like what we added to our whitelist was node 1. Like this is node 1's IP address. So what we really want to do is find a way to convert this IP address to node 1, to like the host name. So this is the IP address. What we want is the host name. And so I'm going to show you like a little quick hack to do that. If you open up POWCoin_2.py, it's like the solution. There's this little snippet that's just like get canonical IP address. At least as far as I'm aware, and I tested this on Windows. This will, and if it doesn't, like let me know, and I'll fix it up so it'll work for you guys. But this just does like a little it looks up the host name, and that will give you like a long thing that will have node 0 somewhere in it, node 1, node 2 somewhere in it, and this just uses a regex to pull out node 0, node 1, or node 2, like the canonical host names we're going for, or we're using. And the reason why we want to use those instead of just the IP addresses is it's just a lot clearer when we're logging stuff, like who's talking to who gets a different message. It's really confusing to have to use, for the same reason that we use URLs and not IP addresses. In this program, we're going to be using the host names and not IP addresses. And so for that, we'll just say for peer here, instead of the client address, it takes client address as a parameter. And so instead of taking client address, we'll say our peer will be get canonical peer address. And now the one other thing we have to do, this imports the regex module here. This uses regex. Okay, so now that we have that set up, let's try to run it. So let's see what it looks like. And so here we go. This is pretty cool. So node 1 woke up first. It tried to connect to the one peer it knew about, node 0. That failed. Node 0 woke up next. It sent connect messages to node 1 and node 2. Node 2 was still offline, but node 1 was not. Node 1 said, okay, I'll accept your connect message. And then when node 0 got the connect dash response message, it says, okay, we're connected. It added it. It moved it from pending peers to peers. It responded with another. It responded with a connect dash response of its own. And then node 1 said, yeah, we're connected. So on both sides, we have a current connection. And so wait a little bit longer. Node 2 wakes up. Node 2 knows about node 0. So node 2 said, hey, let's connect node 0, and the same thing happened. A couple little handshake things, and we are, we have a connection. And so that's pretty cool. But you'll notice that, so node 0 and node 2 are connected. Node 1 and node 0 are connected, but node 1 and node 2 are not connected, right? Because if you remember, in the Docker Compose file, they do not know about each other here. And so this was fortunate that if node 0 wakes up last, well, actually, no, under no circumstances at this point can these two talk to each other. It needs to be basically intermediated by we need to have this peers message so that they can learn about each other. So that's going to be pretty simple. The peers message is, and so let's implement the peers message. That's going to be really simple. And just note how, like here, when we log something from the main thread, this is too long. So I'm just going to show you one little quick hack we can do to make it so that isn't so ugly. At the top of the thing here, when we start the program, we can say threading.current. We can just say main. So that will like override the name. So main thread was what it was. And so that way it'll fit into the like 6 characters of space we give it, or 6 or 7. I'm not sure how many we gave it, but let's look. So yeah, in our logging configuration, we print out the thread name and we say we'll give it 6 characters. And so main is, thread name was 10 characters, THREAD 9 characters, I guess. And so this is 4, so this fits in a little bit better. So that'll improve the output. And then the next thing we got to do, kind of the last thing for this, is we have to implement 2 new messages in our handler. So these would go in the business logic. So they'll be the first 2. So let's say if so this is all we're going to do, and this one's pretty simple. If we get a peers, we're just going to send them a peers response. And we're going to just say, here are our peers. So this just says, hey, these are who we know about, right? If we hop over here, this says just share local peers, and that's what we're doing. We're just looking up the node's peers, and we're sending that in a peers response message. So what do we do when we get a peers response? We just iterate for peer and data, right? Because data is this. Data will be that. For peer and data, node.connect of peer. So we're going to go and send our connect message to them. And that will node.connect. So if we look at the top here, if we look at connect, that will check to see, remember, if they can be connected to it all. So we don't have to do any checks down here. So just because a few different people are calling this, I put the conditions in there, and so that's it. So if we go and run it again, we will remember how node 1 and node 2 did not connect, right? Node 0 and node 2 and node 0 and node 1 connected. Node 1 and node 2 were not able to make a connection with each other. If we fire it up now, I hope if all goes well, we will see that node 1 and node 2 will connect with each other, and we actually have a peer-to-peer network that supports like discovery. Like the nodes are discoverable. Okay, look at this. So node 1 woke up first, and we'll just focus on this initial output. So yeah, so node 1 woke up first. We see some, they were sending connections. So let's just look for the final part. So here's node 0 saying connected to node 1, right? that makes sense because both of these had a connection to each other to begin with. And then this is just this one said, node 0 found node 2, which makes sense. These guys know about each other in the Docker Compose file. And here's the reverse side of that. These are like pairs. And so finally we get, look at this, node 1 sent connect message to node 2. What? How did it find out about node 2? So it looks like when node 1 and node 0 connected with each other, node 0 told node 1 about node 2. That's the only way, right? Well, I just showed you where these two couldn't find out about each other. We could probably like, a little homework. You can do some logging in the like, for example, the peers method, and you can see that it got a peers message, and that's how it found out about node 2. And so it says, hey, node 2, you want to connect? And node 2 says, yeah, I'll connect. And so it looks like this guy found out about the other guy at about the same time and sent one. And at the end, they both connected, and now we have a network. And look at how nicely it's synchronizing. So they all found out about each other. We have we traversed this link in the topology of our network that was kind of invisible before. And so that's cool. That was like we have authentication now. We have discoverability. And I think we made a really big step here with this section of the video. I hope this isn't like too arcane. I mean, we're getting to the point where we're really like building like a node implementation ourselves. And so I hope I'm not pushing you too hard, or like, I hope this isn't too arcane. And if it is, like, make sure to hit me up in office hours, reach out, ask questions, and I'll try to explain anything I didn't hit. But we're really covering some advanced stuff here. I mean, this is really getting to be like how kind of Bitcoin works. So yeah, let me just save the my POW coin. Like, I'm just going to save it here to this. What was it? Yeah, so I'm just going to save it to this file right here. So if you have any problems with this and you want to look up basically a solution to this little increment of the video, just look at this file, and this will have everything up to this exact moment in time that was able to perform this marvelous feat here. Cool. So let's move on to initial block download. So there's one last thing I want to demo before we move on to initial block download, and that is what happens when you try to connect, when you try to send a message and you're not connected. So here's our blockchain just chugging away, our network just chugging away. And so I'm going to send Python my POWCoin.py ping. I'm just going to send a ping message, and we're going to see, hey, was rejected, right? I didn't get a pong back. It was rejected. And so this is like, I think for most of the time, like most of the time, we're probably just going to do this. Pass just means like don't do anything. Or maybe we can just go like this. Like, I think most of the time we're going to want to just we're going to want to leave that uncommented. Let's just comment it out, because sometimes for convenience sake, we'll just want to be able to send a message to our server without having to authenticate. Like to do or practice our sending coins from Alice to Bob and stuff like that. And so I'm just going to show you, like, if you're ever trying to like run something from the command line and it's rejecting you because you can't authenticate, probably the easiest thing to do, just comment that line out and then get I'm not sure why that, maybe is ping not even okay, well, it's working. It's just apparently our if we go down here, we're not doing anything with the result. Like, so this is basically dead code. But so let's just look at Alice's balance. So it'll send us, like, so my point is you can just uncomment out the authentication enforcement, or comment out the authentication enforcement if you want to play around with it. And that's more for like the demo purposes of how you would enforce authentication. But like when you were playing around, sometimes it's just more convenient to comment it out. Now, on to initial block download. Okay, back to the PowerPoint here. Hope you're not too exhausted. I know I'm riding you pretty hard here, but so now we have a way for people to join the network. Let's say they missed 10 blocks, 1,000 blocks, 1,000,000 blocks. They need to catch up, and so this is called initial block download in Bitcoin. It is how you basically the process of requesting historical blocks until you get caught up to where everybody else is. And so this is what we clearly need to do so that it's not a requirement. Like as it is now, the only reason our network works is if all of our nodes spin up and start mining, and basically if all the servers start up before the first block is mined. If any one server fails to start up by the time the first block is mined, they will miss that block, and their chain will forever be out of sync with whoever mined that and whoever else validated that block. So that's the key thing we need to do here is we need to get rid of this like ridiculous constraint so that people can download blocks at any time they want, and you can go offline for a little while. You know, if your computer crashes, or you know, if your internet dies for a little bit or whatever. You know, that's in the real world. These things happen. So we want to allow for this, a little bit of this kind of in theory. Like our protocol is not nearly robust enough to be really useful in the real world yet, but I think it's robust enough for, you know, we're just it's good for demo purposes. So this is what the scheme is going to look like. Another little graph for you. So again, we have node A and B. There are the characters in our play here. And so let's say A is joining the network. Maybe the A just joined. Maybe A just did this, went through this whole thing with node B. And now that it's on the network and it has an empty blockchain, it says, hey, node B, give me your last N, or I'm going to give you my last N block IDs. And it's going to be in this sync message. And what I want you to do is give me blocks in return. I want you to basically fill out my blockchain for me. And so you say sync, you give them the last 50 block IDs, and node B will go and iterate through. You'll go and iterate through your chain in reverse. Basically, you're looking for the most recent block that. You're looking for a block that your peer does not know about, but which builds off a block that your peer does know about. Does that make sense? So you're looking for basically the first thing that will allow you to sort of like tell them something they don't know about. So we'll just read that slowly. Maybe pause the video, read that slowly. It's kind of a lot going on there. And starting with that block, we will send them N blocks. We'll just send them a big message with all these blocks. And so when you get this blocks message containing all these blocks that match this query, you will attempt to one by one add them to the chain, to your chain. And after you're done, if you received N blocks, basically if your node sent you a whole message, if it sent you N of these blocks, if it didn't, if it sent you only 5 blocks, maybe if 5 is less than N, well then you're done with initial block download. If they couldn't find you anything any more than that, then you're done. And so if they were constrained by the size of the message of N, if they were constrained by only being able to send N blocks, they probably have more to send you. So send them another sync message and do this over and over again until you get less than N blocks. That's the protocol here. So it's pretty simple. I mean, and this is basically how Bitcoin works, to be honest. Like Bitcoin doesn't use the last N IDs. It uses the last 10 IDs, and then what it does is it like let's say it uses the 12th ID, then it uses the like the 16th ID. Then it uses the, what would that be? So like the 24th ID or something, or some 22nd. Yeah. So no, yeah, 24th. So it just like squares the distance it goes back, right? So it gets 10 blocks, then it gets, then it goes 2 further back, then it goes 4 further back, then it goes 8 further back, and so it just goes deeper and deeper. And so eventually, the query is very sparse. Once you get to, pretty soon you're jumping by like 1,000 blocks, and you're skipping most of your chain. The idea being that most of the disagreement will happen near the tip of your sinking chain and not near the tail. So probably a little bit too much detail, but we'll actually construct these queries in the second part of the course, where we actually do initial block download for real on the real Bitcoin network, at least kind of the basics. We'll be doing exactly this on the real network. So this is kind of a cool intro to the concept in general on our little thing here. And so that's the next thing we're going to do. It's not relevant. So let's hop over to the text editor and start implementing this. So we are in my POWCoin.py where we started last time, and once again there will be a my POW P2P coin.py. Good God, it's hard to say. So there will be a POW P2P coin underscore, what are we on, 3 .py. That will be the kind of the solution here for, I think I have it, I can pull it up. 3, so there's like a solution file. If at any point you run into a problem and you can't solve it, look at this, and this will only have the small diff of changes, and it's easier to spot where your error might be. And so yeah, and as always, in the Slack group, ask questions. I'm happy to do office hours. I know this stuff is really confusing. It's complex. Don't be afraid to ask for help. So what we're going to do here, what we're going to start off with is we're going to create, just like we did last time. Remember last time we started off by defining this connect function. Now we're going to, and actually this, if you notice, that we no longer use this. You can actually delete this mempool out points. So good to spot that. So we're going to create a def sync, a function, just like remember we did here. It's something you'd call, and it would start. It would connect. This one is just a sync, and so it's going to say it's going to iterate over the peers. It's going to do this. It's going to do this. Send this message. So calculate the last n block IDs, and like you could just send the whole blocks, but it's like kind of, I don't know, it's kind of abuse of the whole idea. If you're really trying to send your peer a query, like these are the blocks I'm interested in, right? And so we don't want to send full blocks. Let's just get the IDs. And so what we're going to say is for peer, let's say, let's get our block IDs first. Well, let's say just to, actually, just doing this for block and okay. Oh, this is a lot going on one line, so I'll break this up. Okay, there we go. So what this does is it says it grabs the blocks. It does a slice of this self.blocks, and so what it does is it let me just show you in the Python shell. So if we open up Python, we'll say like L equals list of range of 20, and so that's what L looks like. And so like let's say we want to get the last 5 elements for L. That's the best way to do it. You say -5 to the end. And so you can, when we do these like slices, you can, if you have a positive number, it counts from the left side. If you do a negative number, it counts from the right side. And so that's what we want to do. We're only caring about the most recent block IDs, right? Because like that's where most of usually our disagreements are going to be towards the tip of the chain. And at least at this point where we have no true like consensus where we're allowed to deviate. At this point, if we don't agree on the tip, then we'll have trouble. We actually won't accept the blocks that our peers give us. So we don't have a way to fork off like block like 16, for example, if this is a chain. If it doesn't build off our tip at the moment, it'll be rejected. So here we got the block IDs of the last 50 blocks, and of course we have to define this get block chunk. Let's just make this 10, so we'll send 10 blocks at a time. This is completely arbitrary. I mean, I think Bitcoin sends like 500 blocks at a time, I think. I forget. Yeah, we'll cover that in the next part of the course, but that's what number comes to my mind. So that would be like 50 megabytes or something. So that'd be like 500 megabytes. That seems like a lot, so maybe I'm wrong. But so once we got the block IDs, we'll say for peer there you go. That looks right to me. Grab the last 50 blocks, grab the IDs of the last 50 blocks, and then basically send them to your peers as the payload of a sync message, like some sort of a query. So the next thing we have to do is let's go over to our other window here and look at the handler, right, for our TCP handler. Like this is the thing that handles the messages we get from other people. So let's create a new message. Maybe we'll stick it right here below ping. It's like sort of it's like the first one of the real transactions, and we'll say or it's the first one of the real messages, the real like dealing with like financial stuff. And we'll say if command equals sync, then we'll say, I'm just going to write a comment out here because this is one of the more like confusing things we do, or it's like you kind of have to wrap your head around it. So I'm going to say find our most recent block peer doesn't know about, but which builds off a block they do know about. Okay, so a 2-sentence comment, 2-liner, that's rare in our programs. Try to keep our comment short and sweet. And so what we'll start off here is we'll say peer block IDs equals data. This, sometimes we just use data because it's we just say data, like we just remember what it is in this context. But here I'm going to break out into a new variable just so it's like a little clearer in our code. And so we will, as we said over here, we're going to iterate in reverse. We're going to iterate backwards, and just because we want to see the most recent. We want to find the most recent thing that they don't know about, right? So it makes sense to iterate backwards, and the way you do that is like this: for block you just do this colon and then -1. So, like for example, L. See, it turns it in reverse. And so one way to copy lists is if you do like double, just colon. This will actually just create a copy. So like L is copy of L is not true anymore. They're equal, but they're no longer the same exact object. They're not like the same reference. And so, I mean, there's other things like you can iterate by a step of 2. So this is like the third parameter in a slice. Like, you can start at the 5th. This is like where you start. This is where you stop, and that's how many you jump by. So this is what we're doing. It's like it's the sort of hidden third parameter in a slice formula. It's like what's your jump, And so here we're just saying I want to start at the beginning and at the end, and I want to jump in reverse by 1. So that's what we're doing, just to give you, for those of you who are newer to Python, a little idea of what's going on there. And so here's where we do our pivotal check. We check if this ID is not in their peer IDs, but that the previous ID of this block is. So we will say if block.id not in peer block IDs, and let's break over to a new line, and block.prev ID in peer block IDs. So can we fit it? No. So that's our condition. We want this block ID to not be in this thing highlighted here means they don't know about this block, but this says they do know about the parent block. And so that'll do the trick for us here. And so at this point we want to find the height of the block. So and then we want to basically take all the blocks from that point to the point get blocks number blocks after. So okay, so there you go. You start your slice at this height, and so you include this block because this is a block we want to know, and then we get we stop our slice, get blocks, number blocks afterwards. So now we have get blocks, number blocks that they don't know about, which build off something they do know about. And so at that point we're going to say let's just say served let's just say that we served the sync request, and this is kind of a rare thing, so maybe it's worth logging it and say we'll log after we actually send. So send so peer and our message. So you'll notice here, so we're sending a message blocks, but at the moment we only have a block message. So what we're going to be doing is we're going to be converting this blocks message that currently only allows you to do one block and just allow a list of blocks. And so in the basic case, you just send a list of 1. And so that's what we're going to be doing. We're just going to be repurposing this message to allow us to send 1 or more blocks at one time. And so at this point, we'll say, we served the request, we found something that works, and we'll say, let's just say return, let's just end. And if we can't, we'll say, if we go through all this and never find one of these blocks, we'll just say logger.info of could not serve sync request. And the reason why we're doing this is actually, so yeah, we're just going to say we could not serve the sync request just as a log message to ourselves in case we need help debugging what the hell's going on. And so at this point, we're going to want to alter this blocks message, and let's just change it right now to blocks. And so what we're going to want to do is let's just say I'll put it here. So let's just say for a block in data, right? So we're getting a list of blocks. Try we'll just see if we can successfully like add the block to our chain, and if we can, we'll set the mining interrupt, which tells our miner to stop. I think we know what this does by now, so I'll leave the comment, and we'll say accept. This will just be like, hey, if this encountered an error, we're just going to assume it was a bad block, and so at that point we'll just say like. Well, we won't. We'll just print out the block ID. So we'll say, hey, rejected block ID. And then last of all, so now we can delete this. We're no longer doing a check like explicitly. We're just doing a check kind of implicitly, because if we can't, if the previous ID does not, if the ID of the block we just got does not build on, if the block we just got does not, we're processing does not build on our chain, this will just raise an error. Hopefully that makes sense. And so we can delete these now. And so if you recall over here, we had this last little part here. If we received n blocks, send another sync message to continue. So let's just do that here. So if len of data node.sync. Just tell it, hey, let's go send another one. We made some progress. Let's keep going. So there we go. Like that basically solves it. Now we just changed the way we do blocks. So let's search our file for any string block, and you'll see it's just in the one place. It's the end of handle block, which does block propagation. And so what we're going to want to do here is we're going to want to change that from a block to a blocks message, and we're going to want to change this from a block to a list of just one block. Just stick square brackets around it. So now we're almost ready to run this sucker. Let's hop down to the end of the file, and we're just going to have to tell it to sync once we get it up. So so before we start the miner thread, after we've joined the network, let's just say time.sleep of 1. Kind of a hack, but like let's just sleep for 1 second while these peer connections come in. Then let's say let's call sync for the first time, and then let's say these are just hacks to like run our program right now. The problem is that like we don't want our miner to start up before we've finished these initial block downloads, because as soon as the miner finds a block, it will break our chain, because we don't have like a intelligent way of resolving conflicts. This is just the simplest way to do it. Like this is code this code and this code will hopefully be able to. We'll find like a slightly smarter way to do it, but it works for now for our kind of demo purposes. So at this point, hopefully we're ready to actually run the sucker. So let's clear this and run. Again, we're using this docker compose p2p.yaml. Let's see what my Docker file is probably. Yep. So again, we run docker compose using this p2p docker compose -p2p.yaml. It's like our new updated version. And let's see what happens. Okay, so there we go. And so one last thing that we want to do here is we want to let's just say at the top of the file here, let's say, let's just say, let's make node 0 sleep 0 seconds, node 1 sleep 1 second, node 2 sleep, or sorry, node 1 will sleep 10 seconds and node 2 will sleep 20 seconds. So this is just a way to like basically make it so when node 2 wakes up, the network has sort of progressed a little bit and it'll have to do initial block download. So now let's try to run this sucker. So node 0 wakes up, it can't connect to anybody, which makes sense. It starts its miner. Mines a block, very good. So now node 2 wakes up, it was able to actually go and it looks like it was able to sync 1 block. And so now node 3 wakes up and it was so yeah, it's actually working. So this just printed out an exception that was fine. We just so it is working. We didn't really get the yeah. I mean, node 2 did a sync of 2 blocks. So here's what we should do. Let's see what our difficulty is. Let's move the difficulty down to 15. Make the problem easier. So we'll spin it up again with the same weights, but with a little easier mining problem, so they'll mine blocks more quickly, and we'll get a little bit more initial block download activity. So here we go. Turned up on a miner. It already has 3 blocks. That's better. 4 blocks. Okay, now another guy goes. So look, he was able. The second node 1 was able to do initial block download of 5 blocks. It got up to speed, and now they're synchronized. So as we go, they're chugging away. And now, so here we go. Like, this is interesting. So node 2 comes along, and while node 2 attempts to do initial block download, it tries to deserialize a message, and it runs out of input. So basically, one of our messages was too long for our to be able to read. So like, it expected a pickle has a specific format, and it was like right in the middle of reading a file, it thought, and then the output stopped. And so what's happening, and so what you see is it caused a chain split. They were not, the node 2 was not able to catch up. And so this is a shortcoming in our the way our protocol works. Like, the way our protocol works is really naive and stupid, and this is kind of a fault on my part. What we were doing is we were just reading like about 4,500 bytes out of the socket. And this is the way we started, and we were always dealing with really tiny messages, so it never became a problem. But right now, we want to basically be able to, we want to read arbitrarily large objects out of this in our protocol. We basically want our protocol to basically start with, a messages should look like this. So the actual bytes of our message, let's say like the first 4 bytes will say how long the message is, and then basically the next 4 bytes, and then the rest of the message is just the message itself. So like, let's say if this first 4 bytes we'll pull out a number maybe like this, right? And the rest, and then so we'll know like, okay, this is exactly how many bytes we need to read, and we could just read them like a certain number at a time until we've basically read the entire length of the message. And that way we never have the problem of reading half a message and basically having our protocol crash like you just saw. So in order to do that, we're going to write a special function called read message. This just will be able to read an arbitrarily long message out of a socket. And so so this is how it'll work. We'll write this right above prepare message here. So And so what this message is going to do is it's going to, I'll just start like, it's going to read the first 4 bytes out of the socket, and it's going to interpret that as a number. And then it's going to just read bytes out of the socket until we've read that many number of bytes out of the socket, basically. And this way we can read kind of large messages out of the socket that are arbitrarily long. So here's where we'll start. We'll say data equals B. This is what we're going to, let's say message. Message is equal to B. And then so, let's say, just a comment and say, so this might be a little confusing, and we'll do a lot more of this type of stuff in the second part of the course, reading from sockets. So consider this as like an intro. We will do a ton of this. You're going to hate me. So what this does is it reads, S is a socket, and so it's going to read 4 bytes out of the socket, and if it doesn't get anything, it's just going to give you the empty byte, which will be 0. So then what we're going to do is we'll say we're going to interpret bytes as an integer, and this is something I'm not going to explain exactly what we're doing here because I will explain this in excruciating detail later on in the course. But you can look it up right now if you want. Int.from bytes just takes bytes, these /x 0 0. These are numbers from 0 to f, the hexadecimal numbers, and this will turn it into an integer. It'll interpret the bytes as integers, right? Like yeah, it'll basically interpret hexadecimal numbers as integers, and where each one of these is like a place, and it uses this thing called big endian, which means like which side of the number are the big, like, the large numbers, and which side are the small numbers. Like, I think big endian means the ones are on the right side. The big endian is like what we usually use numbers with. Little endian means the like ones are on the left, and like the millions would be on the right, and big endian is the reverse. I'm not going to explain it any more than that because it's confusing, and we'll get into that big time later on in the course. And so what we'll say is, message, there's still some message length. We're just going to read a fixed number out of the And so we're just gonna read out of the socket a chunk at a time. I think that chunking it this way will make it a little faster. And you can't just read the whole message length, I don't think, because sometimes the socket, all that, like that message is not actually. Actually, that's probably not true. This is just the way I've seen it done before, and I know it works. So let's just do it this way, and then at the end we will return. We will deserialize these bytes. Sorry, not data. It's message. So. Yep. So we will deserialize it, right? Because that's what we used to do here. That's what when we were reading a fixed number, then we deserialize it. So right now we will say read. I'll just say message equal. So self.request, it's kind of a confusing API, but this is actually the socket because that's what has the .recv method on it. And so yeah, now we just deleted 2 lines of code. delete that comment, and we have this receive message. So one thing that now that we're assuming that our messages are this format where the first 4 bytes say how long the message is. When we send messages, we're going to have to do that same thing. So we'll have to update prepare message. This is the thing that we do to basically prepare a message when we're going to go send it. And so what we'll do here is serialize message equals serialize of message, and then we'll say return we will return the actually no, so we want serialized message and then length. Yeah, so we'll want so this is a little bit of kind of magic, and so what's happening here is, just like we used to do, we have this message format where our messages are just dictionaries, and these things are serialized, which is just we're just pickling it, running it through pickle. And so so that's what we do. We serialize it, we pickle it, and then since it's bytes, we can just take the length of it, right? And then we want to interpret this as we want to turn this integer into bytes, which can be concatenated with the message itself. So we just what we're doing is we're just sticking bytes, a number, 4 bytes that represent some number, and that's sort of like the length of our message. And we just stick that in front of the message, and then so every time we call prepare message, now previously we weren't serializing the message, so now the serialization is happening for us. So let's look for prepare message, and again, I'm kind of glossing over some of this stuff. We'll get into the details and nitty-gritty of this quite extensively later. And so every time we called prepare message, we used to serialize the result. You see, now we're not going to do that anymore because serialization is already happening right here. And so here it happens again, and so we'll get rid of that call to serialize, and let's just make sure that we covered it all. Yep, so that looks like it covers everything. And so there's one more thing I want to do before we run this. If you remember, this is serialize and deserialize. They are imported from utils.py. Utils.py at this point is basically just those 2 functions. So let's stop importing it, and let's paste these functions in, and just so we can see all the code we're using. It's just better to see what we're using, and so we're going to have to import pickle in order to do this. And so at this point, we've imported about half the standard library. Oh well. But yeah, I think this will help us kind of have a little bit better idea what's going on. So, yeah, I think that's enough to run the thing. So I'm going to go over here and let's run it. So node 0 gets online. It manages to mine a couple blocks. Gets 6 blocks. Oh, it's humming away. And so another node 1 gets online. It manages to catch up to node 0. They mine together in sync. And as you see, look at that. So a lot happens and the output's kind of noisy, but let's see where it starts. So here's node 2. Node 2 just got online. It did the handshakes. It got connected. Here it's doing initial block download. Let's see who served it. So node 1 served it the sync request. So it got node height 1, 2, 3, 4, 5, 6, 7. And then here is 8, 9, 10. And then so At 10, it had to go and get another sync request. It couldn't fit it all into one block, so it says, hey, give me 10 more. And so here's 11, 12, 13, 14, 15, 16. And here we go. Look, so after 16, that was up to speed, and now it was able to jump in, and as soon as this next block was mined, it found it. And so if we look a little further, so it continues asking a couple times. It'll reject a couple blocks, but so node 2. Oh yeah, so now look at this. So that's great. So yeah, so node 2 is syncing, and it actually mined this block, right? Node 2 was able to, as soon as it got 16 blocks, as soon as it got to the tip, it was able to mine the next block. That's amazing. And it mined the next block, and it actually mined 3 blocks. Look at that. And yeah, it mined 3 blocks. That's pretty amazing. So yeah, I was able to do initial block download, get caught up, and start contributing as a miner. So that's really awesome. You'll notice that this output is kind of messy. What happens every time we're kind of like gossipy. Every time we get some message that was useful to us, we forward it to all our peers. We don't do any logic to see if, maybe if we just heard this message from a given peer to exclude them. We'll just say no. We'll just basically tell everything that was useful to us, we'll tell to everybody, and we'll just assume they can filter it out if they already know about it. So we're a little gossipy. We have to say, reject block all the time. Maybe we should pull this ID out. Maybe we should pull this ID out because it's pretty noisy. But yeah, I mean, look, we have this blockchain that supports initial block download, right? It had to go, since it was more than 10 blocks, it had to do 2 of these sync requests, and it was able to sync up and lickety split start mining. And so yeah, I think that's pretty awesome. Now we have our you're starting to see that like Bitcoin is a lot more than like a blockchain. It's a lot more than a peer-to-peer network or like there's a lot of different aspects to it. And in order to get like a little working mini demo, I mean, this is like still tiny and naive and stupid compared to the real Bitcoin. You can see there's quite a lot to it, and I mean, I'm not including anything that is superfluous. This is only like the core ideas. I'm trying to keep as much out as we possibly can, just so your mind doesn't explode. But here we've done initial block download. We have done authentication. We have a way to reject messages from people who haven't gone through the proper connection process. We can basically ban peers if we want to. We don't implement any logic to do that, but the one problem is like, let's say if there's any latency between sending these messages, like you'll see pretty soon, like eventually, see now we have chain splits. Eventually 2 people will mine a block at the same time. See here? So they're all at 72 here, 72, 72, 72. Actually, no, here's where the chain split happens. So node 0 and node 1 mine a block at the same time, and I'm not sure, node 2 agrees with one of them. And so when mining continues, then node 0 and node 2 mine the next block at the same height, and basically it looks like node 1 gets screwed. So node 1 was the second node to mine block height 72. So node 2 sided with node 0. Node 1 got left behind, and so if you fast forward now, node 1 is mining at 74 when the other guys are mining at 77. And if you go really far ahead, at this point it's mining 101 when the other guys are doing 137. So it just gets left in the dust because it's got half the hash power as the other two. So yeah, that's just a little overview of where we're at. I'm just kind of riffing here on the state of the project, but we have a little bit more to do. We have a couple little, like 2 little cosmetic changes we want to make, and then after that we'll do our final thing in this video, which is chain reorgs, and that's basically going to be the culmination of this class. Kind of like that's the really big thing we do, and we're still kind of putting all the pieces in for that to make sense. We kind of want to do that last. So before we move on, I just want to. There's a couple tiny little details I want to cover, so that they'll be in this kind of solution file, this POWCoin underscore 3.py. That'll all be in there. So the first thing is this. So when we have send message, we have this like kind of we have this sort of hack that, you know, basically when our command line is sending a message, we do this response, which we have this response parameter, which basically says like keep the socket open and read one message back from it. And this is not optimal. Like ideally we would. So the way our server works is that, the way our system works is that like we don't keep the sockets, we don't keep the connections open for a long time and just send stuff back and forth. We kind of like, with every message, we open up a new connection, send over the information, and then close that connection. And we just check if we know about the peer that, you know, or you know, likewise, if someone sends something to us, they open up a connection and send it over, and then the connection stops. Ideally, we would just have like sockets that were long-lived and would just sit there and allow data to flow in both ways. It was a little trickier to build that, and I've been cribbing off that tiny chain project a little bit, and this is the way they did it in the same way. So yeah, maybe in the future I'll make like an addendum to this course and teach you how to do that. Teach you how to be a little bit more economical about your socket, your connection management. But we are now, this will no longer work. This way of basically when we send a message, be able to say, hey, I want to get a response back. You can just look for this to see where we use it. You know, like for example, in this, it's mostly down here in the command line stuff. You know, when we send a transaction, we will send them like a UTXOs message, try to get the UTXOs, and then we'll say response equals true, so we get a response, so we get the UTXOs back. Mostly because when you're running on the command line, you don't have the ability to just spin up a server. Like that would be sort of like what would be required to get messages in return if we didn't do this. So it's a little bit ugly, but the one thing we need to do here is, now this will not work because we just changed our protocol to be to not just send the message, but to send 4 bytes indicating how long the message is, and then followed by the actual message. And so all we have to do here is just delete this whole thing and say, oops. Just say read message. So just reuse our read message function. Hopefully that makes sense. We can't. The way we read out of a socket has to be the same everywhere, and we changed it, and so we have to change it everywhere. And that's really it. That was just the one little bug I spotted that we would need to connect, take care of before we move on. So I saved this to POWCoin underscore 3.py if you want to check your version against mine, just to make sure we're at the exact same starting point. And yeah, let's move on. Actually, one more thing I want to remember on the output how it was like it would always spit out this, when it said rejected block, it would spit out the ID. That is not really actually of any use to us. So here's where we do it. Let's just change this to just say rejected block and not include any more information about it. It'll just clean up our visual log and make it more understandable, because we don't really care what the ID of the block was unless we're like really deep dive debugging and we actually know what we're looking for, which is probably not the case in most instances here. So check out this file lock.py. It's just in the POWCoin directory. This is a little thing I made to demonstrate the so check out this lock.py function or file I just opened here. It's in the POWCoin directory. It's a little thing I made to demonstrate this problem. So it's a command line tool. It has 3 different modes we can run it in: counter, threaded, and threaded with lock. When we run Python lock.py counter, it'll just run this function here, counter, and it'll print a result. So the way counter works is it refers to this list numbers. Numbers just is a list with 0 in it to begin with, and all it does is it iterates until the last number is 20, and 20 or higher, and it goes and checks that last number and adds 1 to it, then does a little sleep. It sleeps for a random number of seconds between 0.01 seconds and 0.1 seconds. That's all this is, a random sleep. It's just 0.01 hundredth of a second times a random integer between 0 or 1 and 10. And so that's all that does. It's a way to, it sleeps, but it doesn't always sleep the same duration of time. And so then it, this kind of simulates maybe doing a function that sometimes takes a long time, sometimes doesn't take a long time. And then it says numbers, it just appends the value. So all it's doing is just adding another number to the end of the list with a little sleep between reading. This is when it reads the value at the end of the list, and this is when it writes to it, right? So all we're doing is we're sleeping between reading and writing. That's it. And so I'm going to show you that, predictably, this isn't a problem when we run it just as a normal function. Oop. And so I'll show you here, this is not a problem when we run it as a normal function. If you just call python lock.pycounter, it just prints out the first, from 0 to 20. Pretty predictable, right? And so threaded is another, we can run it as we have this like threaded mode, and all that does is calls run of the function counter. So it uses the function counter as an argument to run. And all this does is it starts 10 threads and it waits for them to end. And so how that works in particular is we have a list of threads, and we want this because you want to start all the threads separately and keep track of them, and then for each one wait till it's done, and then we'll print out the final answer, the final output. So it's just kind of a tricky little thing. So for I in range of 10, start a thread that has target equal to target. Target's passed in as an argument, and the argument is counter in this case. And so start 10 threads and run the counter function in this particular case, and then wait for all 10 to stop. And then when that returns, we'll print out what numbers is. So basically counter will be run in 10 threads, and this will be run in the main thread. It'll just print out what the final answer is. And so, it should still work, right? It shouldn't, this shouldn't be any different just because we're running it in threads, right? So let's try it. Holy Lord, it just gets completely obliterated. Look at that. So this code that looked correct is just completely wrong when we run it in a threaded environment. And the culprit is that time.sleep. Basically, when we sleep between reading and writing, maybe while one thread is asleep, a bunch of other threads are reading, and they're all reading this old value. So they're not like atomically reading from the counter, from the numbers, and then writing. They're all reading kind of at the same time, and then they all read kind of old values, and then they all read values, and then they sort of like sleep and then append like an old value to it. And so that's what accounts for the sleep is what accounts for the repeated numbers, but it's even worse than that. We both repeat and we go out of order, right? Because we have a bunch of 2s and now we have a 1. And so the reason for that is that we don't just sleep a fixed amount of time. Like if you just slept, and this is an exercise to the student here, if you just slept 0.01 seconds, well, I'll just show you. So let's just say we just sleep for 0.01 seconds. Yeah, so do you see every single time we have repeats because basically everyone reads a value and they go to sleep and then they write in that old value. They're not seeing they don't see the updates of the other people kind of as they come in. And so that's why you get repeats, but it's the sleeping for a random duration, sometimes longer, sometimes shorter, that gives us the disordering as well. So for example, these guys would all sleep the same duration. Well, over here, this guy slept the least amount of time, and this guy here slept the most amount of time. He probably slept close to 0.1 second because he came in at the very last, right? And so you can sort of see that, if you sleep longer, like these guys have done a lot of, these two threads have done a lot of sleeping because they're like, they're quite a ways behind everyone else at this point. And so yeah, that's the problem. This is the problem basically of writing to. This is an instance of this, like different people writing and reading and writing. The problem of multiple people writing to the same thing without at the same time, basically, without being able to like lock down the thing, the resource when you have access to it. And so I'll teach you a solution for this. All we have to do is when we pass in this argument, this counter function, all we have to do is wrap it in a with counter, basically. And actually, so let's first, I'll just show you. Lock.acquire. This is like the default way of doing it. Say lock.require and then run your function and then lock.release. But the problem is that you have to be, if this raises an error, you got to be clever and always, not clever, you just have to always remember to release the lock. Because if you lock down an important resource like the blockchain and prevent others from using it, that's like your program's just dead. So now we can try, let's try threaded, I think with lock, I think that's what we called it. And so there you go. So that just run with this function, and it calls the same thing. And now just because we are basically locking down access to this resource, we get a nice, we have both no repeats and no out of order. And so yeah, that's I think that's pretty cool. You know, the better way to do it is to go like this. Because this basically takes care of if counter runs into any exceptions, it'll always release the lock once. I'm not going to demonstrate that, but it'll work just the same. And so this is what we need to do in with our chain. And so, you know, in a real production thing, we'd probably want to lock down, you know, like the UTXO set and the mempool. We'd probably want to have more locks. But for this point, we're in our code, we're just going to do the bare minimum. Anytime we write to the blockchain, to node.blocks, we're going to basically demand that they acquire the lock. And so I'm just going to copy this line of code here, and we're going to go to the top of the file, and just below where we create the kind of the global node instance that starts out as none, but the CLI at the end will set it. I'm going to just say there's a lock there, and we've already imported threading because we've used threading a few times now. We use it for we used it in the remember the what was that called? I think in POWCoin, when we had like the round robin, everyone would go with a second in between. You know, they'd wait a few seconds before nominating blocks. That was used in round robin, and then we used it again for the threading. This is how we spin up the two threads. You know, we have the miner and the server, and then we also use this for the whatchamacallit. We also use this as for like the threading event, the event that tells we call it the miner interrupt. This is that tells the miner to stop mining and then go back to, you know, start over, because we just got a new. If the server gets a new block, the server basically goes and tells the miner, hey, stop mining. We got a new block. You're out of date. You need to catch up. So yeah, we already got that import, and just a little reminder, some of the stuff we use that module for. And so let's just look for all the instances of this blocks. So for example, these are reading the blocks, but they're not writing to them. So we're just going to say, like, let's not go overboard, and anytime we see someone reading the blockchain, we'll just kind of let that go. It's more when they write to it. We want to make sure that anytime they're going to be changing it, we want to make sure that they have kind of exclusive access, so you don't have like competing changes. So this is really the thing. Basically, what I'm going to propose is every time we call handle block, because this is the thing that updates our blockchain, I'm just going to say for the whole duration of this function, you have to hold the lock. So let's just search for handle block, and so we only call it twice, right? We call it in mine forever, and then we call it in the server. And so this is all we have to do to make this change. Is, let's say in the server here, we just say with lock, and just indent it one more time. This code is getting awfully ugly, but and I'm sorry, but at least it's pretty simple. We're just going to say, you know, acquire the lock when you're going to do handle block. And one other thing we could do is we could say like with lock here, but then all of a sudden like then this code starts to get like super indented. It's starting to get like, and especially when we do chain reorgs will all happen in this block, in this function. So it's like in Python, you want to try to avoid indenting too much. There's a fancier way we could do it. We could have something like you could have something like with lock. It's called a decorator. This is what you do if you were like writing an actual library. It's a way to like hook in and make the function run exactly the way you want it. You'd have like, yeah, you could do that, but then I don't want to have to teach you. It's called a decorator. I don't want to have to teach you about that. So what we're doing here is like the simplest version. So there's one instance, and let's go find the other one. So it's in mine forever. So right here we'll just say with lock. Do that. So that's pretty simple. So we're not being completely negligent. I just want you to be aware of what can happen when you have two programs running concurrently that try to change the same data, just as the blockchain and the server, or just as the miner and the server do. And this is not like, it's kind of an academic thing. Well, it's not really academic. It's kind of like it's kind of an advanced topic, but like blockchains and Bitcoin are just like heavily concurrent. There's just a lot of stuff. Like this field has a lot of concurrent code, a lot of code that, for example, an initial block download, there's a lot of concurrency. When we write a crawler to crawl the real Bitcoin network, we'll use a lot of concurrency. This is just something we're going to, that's one of the characteristic things of a distributed network, right? Like, you can't assume in a distributed network that everybody has the same kind of time. They won't be able to. Their clocks will all read different things. They'll hear about messages at different times. There's a lot of you can't just assume that everything happens in precisely the order you want to. So I think it's an important thing to understand. And so I'll go and save this. This is only like 2 or 3 lines of code, but let's go and I'm gonna go save this. I'll just ls so. POW coin underscore 4.py. There's some here. This one. There's someone. Got to delete that. So this one here is where I saved this file. It's only. I'll just show you like diff. Right. So there's only a few. There's only a few lines that changed here, and so. But we're going in baby steps, so that's good. So then the next one, we'll start working on this kind of P2P coin underscore 5. That'll basically be like the final, be close to the final thing we do. So let's hop into that right now.